Imagine placing a spacecraft inside a furnace hot enough to melt steel. Most people would assume the outcome is obvious. The metal would soften, structures would fail, electronics would be destroyed, and within minutes, the vehicle would become little more than a glowing mass of debris. Yet every time astronauts return from orbit, they deliberately fly into an environment that seems to approach exactly that scenario. For a brief period during re-entry, temperatures around a spacecraft can climb beyond 1,650 degrees Celsius. Outside the windows, if there are windows at all, the darkness of space disappears behind an expanding shell of incandescent gas. Communication signals often fade. The vehicle begins to shake. Layers of atmosphere that seemed impossibly thin from orbit suddenly become a wall of resistance, powerful enough to drain enormous amounts of energy from an object moving faster than a rifle bullet many times over. At first glance, the mystery appears simple. How can anything survive that much heat? But the deeper engineers studied the problem. The stranger the question became, because the most important challenge of re-entry is not actually temperature. That sounds almost absurd. After all, temperatures measured around a returning spacecraft can exceed those found inside many industrial furnaces. Yet temperature alone does not tell the whole story. In engineering, what ultimately matters is how energy moves, where it moves, and how quickly it arrives. A spacecraft, returning from orbit, is not merely encountering hot air. It is carrying an enormous reservoir of kinetic energy accumulated while traveling around Earth at roughly 28,000 kilometers per hour. That energy has to go somewhere. The atmosphere becomes the mechanism that forces the conversion. Motion transforms into heat on a scale difficult to visualize. Every second, vast amounts of energy are being dumped into the surrounding air. The glow visible during re-entry is not simply a vehicle getting hot. It is evidence of a violent energy exchange taking place between a machine built by humans and the physics of an entire planet. This creates an unexpected paradox. Space itself is often imagined as the most dangerous thermal environment imaginable. Yet spacecraft spend months operating in orbit without bursting into flames. The true thermal crisis begins only when they come home. Returning to Earth, not leaving it, is where some of the most severe heating conditions occur. Even more surprising is the fact that engineers do not solve this challenge by making spacecraft indestructible. The history of re-entry is not a story about building the strongest metal ever invented. In many cases, the winning solution involves materials that intentionally erode, crack, char, vaporize, or sacrifice themselves in carefully controlled ways. To someone unfamiliar with aerospace engineering, that sounds like failure. To a spacecraft designer, it can be the difference between survival and catastrophe. The closer we look, the more the familiar image of a spacecraft changes. What appears to be a simple vehicle falling through the sky is actually participating in one of the most extreme engineering events ever performed routinely by humans. For a few critical minutes, every decision made by designers, physicists, materials scientists, and mission planners is tested against forces that cannot be negotiated with, and temperatures that seem impossible to endure. And hidden inside that fiery descent is a discovery that completely changed how engineers think about heat, motion, and survival. One of the most persistent misconceptions in the history of aerospace engineering emerged long before the first astronaut ever reached orbit. It came from something so familiar that almost nobody questioned it. If an object moving through air becomes hot, then friction must be the cause. The idea seemed obvious because it matched everyday experience. Rub your hands together and they warm up. Strike a match and friction helps ignite it. Watch a meteor streak across the night sky, and it appears to be burning because it is scraping against the atmosphere. For decades, even many educated observers imagined that re-entry heating was simply an extreme version of the same phenomenon. The faster something moved, the more friction it created, and the hotter it became. Yet, as engineers began studying the problem seriously during the 1940s and 1950s, the numbers refused to cooperate with that explanation. Wind tunnel experiments, high-speed flight research, and theoretical calculations started revealing something unexpected. At the velocities involved in orbital flight, air behaved in ways that felt almost counterintuitive. Instead of smoothly flowing around a vehicle, the atmosphere became compressed so violently that it transformed into an entirely different environment. This distinction mattered because it changed where engineers looked for solutions. If friction alone were the enemy, smoother surfaces might have solved much of the problem. But many of the earliest researchers gradually realized they were confronting something deeper than surface rubbing. They were confronting the behavior of gases under extreme compression. The challenge became even more confusing because humans had no direct experience with speeds anywhere close to orbital velocity. The fastest aircraft of the early jet age traveled only a fraction of the speed required for spaceflight. Existing engineering intuition was built on airplanes, not spacecraft. What worked for a fighter jet did not necessarily work for a vehicle returning from orbit. In fact, some of the design choices that made aircraft efficient could become liabilities at much higher speeds. During the early years of rocket development, several engineers believed that sharp, streamlined shapes would naturally be the best solution. After all, aviation had spent decades reducing drag through sleeker designs. It seemed logical that a spacecraft should be as aerodynamic as possible, but calculations performed by researchers such as H. Julian Allen at the National Advisory Committee for Aeronautics suggested the opposite. Surprisingly, blunt shapes often generated less dangerous heating than sharp ones. The reason sounded almost backwards. A rounded front could push the hottest shock layer farther away from the vehicle itself, creating a buffer zone between the most intense thermal environment and the spacecraft structure. This was a moment when intuition and physics parted ways. A design that looked less aerodynamic on paper could actually be safer during re-entry. Similar misunderstandings appeared in public discussions as well. Newspaper illustrations frequently depicted spacecraft as giant bullets slicing cleanly through the atmosphere. The reality was far stranger. The atmosphere was not merely an obstacle to pass through. It became an active participant in the process, reshaping energy, generating shock waves, and creating conditions unlike anything encountered in conventional flight. By the late 1950s, engineers increasingly understood that the real challenge was not simply finding a stronger metal or a thicker wall. The assumptions inherited from traditional aviation were proving inadequate. Every new experiment seemed to reveal another layer of complexity, hidden inside what initially looked like a straightforward heating problem. And as researchers dug deeper into those results, one particular discovery began to stand out, a discovery that would completely alter the way spacecraft were designed from that point forward. The breakthrough did not arrive in the form of a revolutionary engine, a new metal, or a dramatic technological leap. It emerged from a realization that seemed almost uncomfortable to engineers trained to make machines stronger. What if survival did not require resisting the heat at all? What if the solution was to let part of the spacecraft disappear? During the 1950s, as the United States accelerated its efforts to reach space, researchers faced a practical problem. Theoretical calculations were becoming increasingly clear about the severity of re-entry, but calculations alone could not bring astronauts home safely. Engineers needed materials capable of enduring an environment that no conventional aircraft had ever encountered. Many early approaches focused on insulation. The logic was straightforward. Build a barrier thick enough to keep the heat out. Yet every additional layer added weight, and weight is one of the most expensive commodities in rocketry. A heavier spacecraft requires a larger launch vehicle, more fuel, and more complexity. The problem quickly became a balancing act between protection and practicality. Then researchers began experimenting with materials that behaved in a completely different way under extreme temperatures. Instead of remaining intact, these materials decomposed. At first glance, that sounded disastrous. In most engineering disciplines, material degradation is considered failure. But under the unique conditions of re-entry, something remarkable happened. As the surface layer heated up, it started to char, melt, crack, vaporize, or release gases. In doing so, it carried energy away from the spacecraft. The material was sacrificing itself, but the sacrifice was controlled and predictable. Rather than trying to stop the heat entirely, it was actively removing thermal energy from the system. This concept became known as ablation, and it transformed spacecraft design. Imagine holding an ice cube in your hand. The melting ice absorbs energy as it changes state. Now imagine a material engineered to perform a far more sophisticated version of that process under extreme conditions. Every tiny fragment that broke away, every molecule that vaporized, carried energy with it. The heat was no longer attacking a passive wall. It was interacting with a dynamic protective layer designed specifically to consume and redirect that energy. NASA's early Mercury capsules became some of the first practical demonstrations of this idea. The blunt heat shield mounted beneath the spacecraft was not expected to remain pristine. Engineers fully anticipated that portions of it would burn away during re-entry. In fact, visible erosion was evidence that the system was working exactly as intended. This represented a profound shift in engineering philosophy. Instead of building a structure that survived unchanged, designers intentionally created components that would be destroyed in a carefully managed manner. There was elegance in that approach. The spacecraft did not need to win a battle against physics. It only needed to guide the process in a predictable direction. The same principle soon appeared throughout the emerging space industry. Material scientists developed increasingly sophisticated ablative compounds. Chemists studied how resins, fibers, and carbon-rich substances behaved at extreme temperatures. Engineers learned to calculate not only how much material would disappear, but exactly where and how quickly it would do so. Re-entry was gradually becoming less of an unsolved mystery and more of a controlled engineering event. Yet even as ablative heat shields proved their value, they raised another fascinating question. If engineers could deliberately manipulate the flow of thermal energy using materials, could they also manipulate the flow itself, long before it ever reached the spacecraft? The answer begins with a simple fact that is easy to overlook because it happens invisibly. A spacecraft returning from orbit is not flying through the atmosphere in the same way an airplane flies through the atmosphere. At orbital speeds, the air ahead of the vehicle cannot move out of the way fast enough. Instead, it becomes trapped, compressed, and violently squeezed into a thin region in front of the spacecraft. This is where the real story unfolds. Compression is one of the most powerful heating mechanisms in nature. Anyone who has used a bicycle pump has experienced a mild version of it. Pump air rapidly into a tire, and the pump body becomes warm. The air molecules are forced into a smaller space, their energy increases, and temperature rises. Now imagine that process occurring not at a few kilometers per hour, but at nearly 8 kilometers every second. The result is a layer of gas heated to extraordinary temperatures before it ever touches the spacecraft. This creates a shock wave, an invisible boundary, where the properties of the airflow change almost instantly. On one side, the atmosphere behaves relatively normally. On the other, pressure, density, and temperature surge to levels rarely encountered on Earth. The shock wave becomes one of the defining features of re-entry physics. In many ways, the spacecraft is not interacting directly with the atmosphere at all. It is interacting with a highly altered environment that its own speed has created. As temperatures continue to rise, the gas undergoes another transformation. Molecules begin to break apart. Oxygen and nitrogen no longer remain comfortably bound together. Electrons are stripped away from atoms. The gas becomes plasma, often called the fourth state of matter. This glowing envelope is responsible for the fiery appearance associated with re-entry. It is also the reason communication blackouts can occur. The electrically charged plasma can interfere with radio signals, temporarily isolating a spacecraft from the outside world during some of the most critical moments of its descent. Yet another misconception emerges here. Seeing temperatures of 1,650 degrees Celsius or more naturally leads people to imagine that every part of the spacecraft instantly reaches the same temperature. In reality, temperature and heat transfer are not identical concepts. A blast furnace and a spark from a fire can have similar temperatures, but they deliver energy in dramatically different ways. Engineers care less about the number itself and more about how much thermal energy crosses into the structure over time. This distinction becomes the foundation of thermal protection design. The challenge is not merely surviving a hot environment, it is controlling the flow of energy from an extremely hot environment into sensitive components that must remain functional. Every material responds differently. Some conduct heat rapidly, others slow it down. Some absorb energy and store it, others release it through chemical reactions or physical changes. Re-entry design becomes an exercise in directing these processes with extraordinary precision. The shape of the vehicle also plays a surprisingly powerful role. A small change in geometry can alter the location of the shockwave, the distribution of pressure, and the amount of heat reaching different areas of the spacecraft. What looks like a simple curved surface is often the result of decades of aerodynamic research and computational modeling. Engineers are not merely designing a shell. They are shaping the behavior of the atmosphere itself, influencing where energy concentrates and where it dissipates. The spacecraft survives, not because it ignores the laws of physics, but because every aspect of its design works with them, turning an apparently hostile environment into something that can be predicted, managed, and increasingly controlled. The remarkable thing about a modern spacecraft is that much of its survival strategy is already decided long before re-entry begins. By the time the vehicle encounters the upper atmosphere, engineers have spent years determining exactly how it should be oriented, how quickly it should descend, which surfaces will face the greatest thermal loads, and how energy will be distributed across the structure. Re-entry is often portrayed as a dramatic plunge toward Earth, but from an engineering perspective, it is a carefully choreographed energy management process. Every angle, every contour, and every material serves a specific purpose. Consider a capsule returning from orbit. As it descends, the broad underside is intentionally pointed into the airflow. This is not simply a protective shield attached to the spacecraft. In many designs, it is the spacecraft's most critical component. The geometry creates a stable, aerodynamic configuration while simultaneously controlling how the shockwave forms around the vehicle. The goal is not to eliminate heating, but to manage where it occurs. Engineers would rather concentrate extreme conditions in locations specifically designed to handle them than allow heat to spread unpredictably across the entire structure. Beneath the outer surface lies a carefully engineered hierarchy of materials. The first layer may experience temperatures that would destroy conventional aerospace components, yet directly underneath it, temperatures can be dramatically lower. This thermal gradient is one of the most important achievements in spacecraft design. The outer layers absorb, redirect, or remove energy, while deeper layers slow the rate at which heat migrates inward. By the time thermal energy reaches the crew compartment or sensitive electronics, it has often been reduced to levels that can be handled through more conventional insulation systems. The process becomes even more sophisticated when active guidance enters the picture. Early spacecraft largely followed predetermined trajectories once they entered the atmosphere. Modern vehicles can continuously adjust their orientation during descent. Small changes in attitude can alter aerodynamic forces, allowing the spacecraft to control both its path and its heating profile. In effect, the vehicle can steer through the atmosphere in ways that influence how rapidly kinetic energy is dissipated. This capability allows engineers to spread thermal loads over longer periods rather than concentrating them into a single, extreme event. Some spacecraft also use controlled lifting flight during portions of re-entry. Although they are not airplanes in the traditional sense, their shape generates enough aerodynamic lift to modify the descent trajectory. This provides additional flexibility, enabling mission planners to target specific landing zones while managing structural and thermal stresses more effectively. The atmosphere becomes something more than a barrier. It becomes part of the spacecraft's braking system. The contrast between different spacecraft designs reveals how diverse these solutions can be. The Apollo capsules relied heavily on ablative materials that gradually eroded away. The Space Shuttle pursued a radically different approach, using thousands of lightweight silica-based thermal protection tiles that remained attached to the vehicle. Each tile was individually engineered for its location, because heating conditions varied across the spacecraft. Areas experiencing the highest temperatures required entirely different protection strategies than regions exposed to lower thermal loads. Today's spacecraft often blend lessons from multiple generations of engineering. Vehicles such as Crew Dragon and Orion incorporate advanced ablative systems refined through decades of research, while newer programs explore reusable thermal protection technologies intended to support more frequent missions. Behind every approach lies the same reality. Survival depends on understanding not just materials or aerodynamics alone, but the interaction between them. The most successful designs emerge when engineers stop thinking of the spacecraft as a rigid object moving through the atmosphere and begin treating it as part of a larger system in which airflow, energy, structure, and time are all interacting simultaneously. And once that perspective takes hold, it becomes possible to imagine what happens when engineers push those interactions to their absolute limits. To understand just how far engineers have pushed re-entry technology, it helps to look at the missions that stretch the laws of physics closest to their practical limits. Not every spacecraft returns to Earth under the same conditions. The amount of energy that must be managed depends heavily on where that spacecraft is coming from. A vehicle descending from low Earth orbit is already facing an enormous challenge. But once missions begin venturing beyond Earth orbit, the numbers change dramatically. The most famous example remains the Apollo program. When Apollo astronauts returned from the Moon, they were not merely falling back to Earth. They were arriving from nearly 400,000 kilometers away, carrying far more kinetic energy than a spacecraft returning from the International Space Station. At peak re-entry, Apollo capsules approached Earth at roughly 39,000 kilometers per hour. That increase may not sound enormous compared to orbital speeds, but energy does not scale in a simple, linear way. Small increases in velocity can produce disproportionately large increases in the thermal loads that engineers must manage. The Apollo heat shield became one of the most remarkable pieces of engineering of the 20th century, absorbing conditions far beyond anything encountered during conventional orbital missions. Yet even Apollo was not the fastest object humanity has ever brought home. Several robotic missions returning scientific samples from deep space have entered Earth's atmosphere at even greater speeds. NASA's Stardust capsule, which returned samples collected from a comet, entered the atmosphere at approximately 46,000 kilometers per hour. For a brief period, it experienced some of the most intense re-entry heating ever faced by a human-made object successfully recovered on Earth. The engineering challenge was extraordinary because there were no astronauts aboard to intervene if something went wrong. Every aspect of the thermal protection system had to function exactly as designed. Then there was the Space Shuttle, a vehicle that represented a completely different philosophy. Unlike capsules that relied primarily on sacrificial heat shields, the shuttle was designed to fly again and again. Its thermal protection system consisted of more than 24,000 individual tiles and reinforced carbon-carbon structures, each tailored to specific thermal environments across the vehicle. Some regions experienced temperatures high enough to glow visibly during descent, while other sections faced comparatively moderate heating. The shuttle effectively turned re-entry into a reusable engineering problem, something many experts had once considered nearly impossible. Today, attention increasingly focuses on vehicles intended to support large-scale space transportation. SpaceX's Starship presents a challenge unlike anything that came before it. Its immense size means engineers must manage thermal protection across a vastly larger surface area while maintaining rapid reusability. Instead of relying entirely on traditional ablative systems, Starship employs thousands of ceramic heat shield tiles designed to survive repeated missions. The scale alone is staggering. Every tile must remain attached, properly aligned, and capable of enduring extreme thermal cycling. Looking beyond Earth, engineers face even stranger environments. Mars missions introduce a different problem because the Martian atmosphere is thick enough to generate dangerous heating but too thin to provide the same level of aerodynamic braking available on Earth. Spacecraft arriving at Mars often encounter what engineers sometimes describe as a difficult middle ground. Too much atmosphere to ignore, not enough atmosphere to fully exploit. This challenge has driven research into inflatable heat shields, supersonic decelerators, and entirely new entry systems. Each mission becomes a reminder that re-entry is not a single engineering problem, but a family of related problems, each shaped by different worlds, different velocities, and different limits. And the farther humanity pushes into the solar system, the more those limits begin to reveal where today's solutions may eventually stop being enough. The most revealing moments in engineering often occur when a system fails. Success can demonstrate that a design works, but failure exposes why it works. In the world of atmospheric re-entry, those lessons are rarely gentle because the margins are so unforgiving. A spacecraft traveling at hypersonic speed carries immense energy, and once re-entry begins, there is little opportunity to correct a serious problem. The laws of physics continue operating with complete indifference to human intentions. One of the most important realities engineers learned is that catastrophic failure does not necessarily begin with extreme temperatures everywhere. Often it begins with a tiny defect in a very specific location. A gap measured in centimeters can become the starting point for a chain reaction that unfolds at thousands of kilometers per hour. Thermal protection systems are designed around the assumption that heat will follow predictable pathways. When those pathways change unexpectedly, conditions can escalate with surprising speed. This principle became tragically clear during the loss of Space Shuttle Columbia in 2003. During launch, a piece of insulating foam broke away from the external tank and struck the leading edge of the left wing. The event appeared relatively minor at the time. Foam was lightweight, and similar shedding events had occurred during previous missions. Yet velocity changed everything. Even a low-density object can carry substantial energy when moving at high speed. The impact damaged part of the reinforced carbon-carbon thermal protection system protecting the wing's leading edge. During re-entry, superheated plasma entered the breach. Once inside the wing structure, the thermal environment evolved beyond what the vehicle was designed to tolerate. Internal components weakened, structural integrity deteriorated, and eventually, the spacecraft broke apart. What makes Columbia particularly significant is that the disaster was not caused by a complete failure of the thermal protection system. Most of it performed exactly as intended. The loss resulted from a localized vulnerability that allowed heat to reach an area never meant to experience such conditions. The event reshaped how engineers think about inspection, risk assessment, and damage detection. Similar lessons have emerged from unmanned missions as well. Throughout the history of spaceflight, several spacecraft have been lost because entry angles were slightly incorrect. Enter too steeply and heating rates rise dramatically, while structural loads increase. Enter too shallowly and a vehicle may skip off the atmosphere rather than descend safely. Re-entry exists within a surprisingly narrow corridor. Engineers sometimes compare it to threading a needle while moving at several kilometers per second. The challenge is not only thermal. Aerodynamics, navigation, guidance, and structural design all become intertwined. Even modern computational models have limits. Engineers can simulate extraordinary conditions, but no simulation perfectly captures reality. Materials behave differently after years in space. Tiny manufacturing variations can influence performance. Unexpected interactions occasionally emerge during flight. This is why testing remains so critical. Wind tunnels, arc jet facilities, plasma chambers, and high-temperature material laboratories exist because engineers understand that theory alone is not enough. Every generation of spacecraft is, in some sense, a conversation between prediction and reality. Yet perhaps the most fascinating lesson is that failure rarely arrives as a dramatic confrontation with a known limit. More often, it emerges from the interaction of multiple small factors that appear manageable when viewed individually. A minor impact, a subtle material weakness, an overlooked assumption, a slightly different trajectory. Re-entry remains one of the most demanding environments engineers routinely face because it leaves so little room for uncertainty. And as future missions grow larger, faster, and more ambitious, those uncertainties become increasingly important to understand before they reveal themselves the hard way. For all the progress made over the past several decades, re-entry remains a problem that engineers have not fully conquered. They have learned how to manage it, predict it, and survive it with remarkable reliability, but the underlying challenge grows more difficult every time humanity attempts something more ambitious. The reason is simple. The physics that govern re-entry are tied directly to energy, and energy increases rapidly as missions become faster, larger, and more distant. The techniques that work for today's spacecraft may not scale indefinitely into the future. One of the clearest limits involves materials themselves. Every thermal protection system eventually encounters temperatures, pressures, and heating rates beyond what it was designed to withstand. Engineers can improve ceramics, carbon composites, and ablative compounds, but no material possesses infinite tolerance. At sufficiently high velocities, the thermal environment becomes so extreme that traditional approaches begin approaching their practical limits. This challenge becomes particularly relevant when scientists consider future sample return missions from distant planets, high-speed interplanetary transport, or concepts involving much faster travel through the solar system. Some researchers are already exploring solutions that sound more like science fiction than conventional aerospace engineering. One idea involves actively cooling portions of a spacecraft during re-entry, rather than relying solely on passive protection. Instead of merely resisting heat, the vehicle could circulate coolant through critical structures, carrying energy away before temperatures become dangerous. Similar principles are already used in advanced rocket engines, but applying them to large-scale re-entry systems presents enormous engineering challenges. Every kilogram of coolant adds weight, complexity, and potential failure points. Another area of research focuses on manipulating the surrounding flow itself. Since much of the thermal environment originates from the behavior of the gas around the spacecraft, some engineers have investigated whether magnetic fields might influence plasma during extreme re-entry conditions. In theory, a sufficiently powerful magnetic field could alter how charged particles move near the vehicle, potentially reducing heat transfer in certain regions. Whether such systems will ever become practical remains uncertain, but the fact that researchers are exploring them illustrates how seriously future missions may push existing technologies. The challenge becomes even more interesting when viewed through the lens of reusability. Historically, many thermal protection systems were designed to survive a single mission. Modern spaceflight increasingly favors vehicles capable of flying repeatedly with minimal refurbishment. This shift changes the engineering priorities. A system that works perfectly once may be economically impractical if it requires extensive replacement after every flight. The future may depend as much on maintenance, durability, and operational efficiency as on pure thermal performance. At the same time, entirely new destinations continue forcing engineers to rethink old assumptions. Returning from Mars presents one set of constraints. Returning from the outer solar system would present another. Worlds with different atmospheres create entirely different aerodynamic and thermal environments. A solution optimized for Earth may perform poorly elsewhere. In many ways, every planetary atmosphere represents its own engineering puzzle. And yet, beneath all of these future technologies, ambitious missions, and evolving designs, the central insight remains surprisingly elegant. A spacecraft does not survive re-entry because it is stronger than 1,650 degrees Celsius. It survives because engineers learn to understand the flow of energy deeply enough to shape its path. The fiery plasma, the shock waves, the thermal protection systems, the carefully calculated trajectories, all of them exist for the same reason. The atmosphere is not simply something a spacecraft passes through. It is part of a carefully managed interaction between motion and heat, between physics and design. The question that once seemed impossible, how a spacecraft survives temperatures capable of melting steel, turns out to have an answer that is both more subtle and more fascinating. The spacecraft does not defeat the heat. It survives by convincing the heat to behave in ways that humans have spent generations learning to predict, control, and increasingly engineer to